So is my screen visible to all of you?
Yes,
And I'm audible, right? Hello?
yes, sir, yes, sir. Yeah.
Okay. So welcome everyone to the week 9 discussion of this course, Deep Learning, and this course was originally taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering of IIT Ropar. Myself, Ayan Paul, I am a PMRF research scholar from IIT Kharagpur, and I am a PMRF TA of this course. My duties are I will solve some of the question that will be very similar to your assignment problem, so that whenever you will be solving assignment problem, you will not feel it's something new. Okay, so before that I always prefer to have the summary of the week before discussing the problem. That will be more convenient whenever we are actually solving the problems. Okay, so let's start with the discussion. Okay, so till week 1 to week 8 we have covered all the theories related to this neural network. From week 9 to week 12, what we will do is going towards the application part. Okay, so week 9 today we have this application regarding NLP. What is NLP? NLP is this natural language processing. Okay, this is a part, or you can say a subfield of AI, which enables the computer to understand, interpret, and generate human language. Okay, so we will be discussing more of this. Why we are doing this? First, this NLP is a very important subfield of the AI, and second, in terms of application, and second we also want to know how we can apply this neural network that we have learned so far in this NLP problem. Okay, so first thing, starting with the discussion, what is the requirement of vectorial word representation? Okay, so always whenever you are taking any type of review or anything, you will be receiving inputs in the terms of sentences or documents like that. Okay, so, for example, like you have this new movie released. Okay, whenever you will be asking people how is the movie or how you like the movie, they will be giving you some opinion, right? So that opinions will always be opinion will always be in the terms of some sentences. Okay, so what you need to do is, if you need to rate the movie out of 10 or whatever the number, let's say out of 10. So what you have to do is you have to decode those statements. Okay, if you are asking how you like the movie, someone will say good, someone will say yeah, very good, someone will say it was interesting, like that. Okay, now you will be asking how is the cast for the movie, someone will say good, someone will say I need this actor but this actor was not present, like that. If you will ask about the length of the movie, again there will be some opinions like, yeah, it was very long movie, it was a good movie but it was a long movie, type of things. Okay, so what if we want to just rate the movie, what we want to do is we want to have a mathematical relationship. Okay, any neural network or machine learning, any type of learning, what you will do is you will always want to establish a mathematical. Okay, someone is joining. Okay, so always you want to establish a mathematical relationship, okay, between the mathematical relationship between the input and the output. Okay, so input now is in the form of sentences. Okay, so that is why our requirement is that is why we require this vectorial word representation. Okay, because first we want our inputs to be in the form of some numbers, and from that numbers we want to achieve our output. Okay, so that is why we require this vectorial word representation. Okay, so this is the concept of this. Now how we do the vectorial word representation? We use this one hot representation of word. what is this one hot representation of words? So before that, you have to understand this term known as corpus. Okay, very important term, corpus. Okay, you will always hear this term again and again if you are doing this NLP or any other such thing. So what is this corpus? Corpus is all the sentences or all the sentences that you are interested in. Okay, very simple term. If I want to decode what is the corpus, so it is all the sentence or all the documents that are provided. Okay, so that is corpus. Now from that corpus, our first step is always to extract the vocabulary of the corpus. How we can extract the vocabulary? So corpus is a group of sentences or all the sentences that is present in a document. So first you will write all the sentences. Now you will extract the vocabulary. How you can extract the vocabulary? You will write all the words side by side. Okay, and then what you want to ensure is that you will not repeat the words. Okay, you will only in the vocabulary you will only have set of unrepeated words or unique words. Okay, that you have to ensure that. So once you have corpus, you will be forming the vocabulary. Now once you form the vocabulary, you just have to do the representation in terms of this one hot representation. So what is this one hot representation? So what you will do, how many words or unique words in the vocabulary you have, you will put all this in the form of a number. What number? Either 0 or 1. Okay, so like that we have 15 number of words, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Yeah, we have 15 number of words. So our vocabulary will be this vector of size 15. Okay, now in this 15, if I want like this machine, so where is my machine? Machine is in the second position. So in second only I will write 1, other position I will write 0. So that is one hot encoding, means one the word which position the word is present, that position we will be encoding 1, all other position we will be encoding 0. So by this we can convert our this sentences or this word into a vectorial representation. So this is known as one hot representation of words. Okay, now what is the limitations? That is the main question. Now what is the limitation? We have encoded it, but what are the limitations? So the first limitation is the size of vocabulary, because here the corpus you are seeing, it is only like 4 sentences, but whenever we are doing this natural language processing, we require like we are taking data from big documents like this. For example, this data set, like this PTB data set or this Google data set, this will have 13 million plus words in the vocabulary. Okay, so that is a problem, because we have the size of the vocabulary is the first problem. Second problem is, in all this one hot representation of word, what you are seeing this, we cannot find the similarity between the two words. Like the cat and dog and truck, we know this cat and dog are some sort of similar, but this truck is not similar to cat and dog. Okay, but whenever you will do the similarity part, you have whenever you will be finding the similarity part between the cat, dog and truck, the similarity will always be the same. What will be the similarity? If we want this cosine similarity, what is this cosine similarity? Cos of alpha, right? Cos of alpha is the product between the two vector, like v1 dot v2 divided by v1 mod and v2 mod. Okay, this is the cosine similarity. So let's say we want to have the cosine similarity between cat and dog. We will do the dot product, and whenever we will do the dot product, the answer will come 0, because the position in the second position in this vocabulary, the second position is assigned for dog, that is why 1. But in the cat vocabulary, the 1 2 3 4 5 6 position is assigned for cat. Okay, so whenever you will multiply this, your answer will always come 0, or the cosine similarity will always come 0. Also you can find out this Euclidean distance between the two words, and for any two words the Euclidean distance will always come always come like root 2. Okay, so that is the thing. Euclidean distance and cosine similarity, we cannot find any similarity between two sets of words which are close to each other. Or actually for this Euclidean distance between cat and dog should be less, and the Euclidean distance between dog and truck should be more. But in this one hot representation of word, we cannot achieve this. All our Euclidean distance will be root 2, and all our cosine similarity between two words will be 0. So that are the two problem. Again I am repeating, one problem is the size of vocabulary, because here we are only dealing with a small corpus. So yeah, we can write this as a one hot encoding, but whenever we are processing a large vocabulary like this Google dataset, etc., this will have so many words, like more than 13 million words. So for that this is a problem, because we have a large size of vocabulary, so that will be consuming more memory, and it will be difficult to process. Second difficulty what we have is like every word, the relationship or between every word in this one hot encoding, it is always the similarity between every two words in this one hot encoding is always the same, that is 0. And the Euclidean distance will always be root 2. So we cannot find out, like cat and dog, we know, human perspective, we know the cat and dog are similar, but dog and truck or cat and truck is not similar. So but in this one hot representation of word, we cannot find this similarity. Okay, so this is the limitation of this one hot representation of word. Okay, so is this clear to all of you? Am I audible?
How to calculate the Euclidean distance, sir?
Euclidean distance, how, what is Euclidean distance? Euclidean distance is okay, yeah, Euclidean distance is root over x1 minus x2 square, x1 minus x2, okay, x2 square plus y1 minus y2 square
Okay.
plus z1 minus z2 square, like that, dot like that. So how we will find the Euclidean distance between the cat and dog? Root over 0 minus 0 whole square plus 0 minus
0
1
minus
whole
1
square,
whole square.
0 minus
Okay.
0, 0 minus 0, 0 minus 0,
1 minus
1
0 whole
minus 0,
square.
and 0
0
minus 0
minus
whole
z0.
square. So every time whenever you will be find the Euclidean distance between any two words, that will always come root 2. Okay, so that is a problem. And whenever you will be finding the cosine similarity, that will always come 0. Okay, so that is the problem of one hot representation of words, because here we know the cat and dog are similar, right? So Euclidean distance should be less and the cosine similarity should be more in case of cat and dog, whereas in case of cat and truck, the cosine similarity should be less and Euclidean distance should be more. But in one hot representation of word, all the Euclidean distance are same and all the cosine similarities are same whenever we are comparing the two words. Okay, so that is a disadvantage of this one hot representation of words.
So
Disadvantage or limitations. Yeah.
the cosine similarity, what is the formula, sir?
Cosine similarity, how you can find the cos alpha? Cos alpha is v1 vector dot v2 vector divided by v1 mod v2 mod, right? So here let's say this is your v1 vector, okay, and this is your v2 vector. So you just do the dot product, and whenever you will be doing the dot product, the answer will always come 0 0 0 0 0, right?
Okay.
So that is the thing. So that is why cosine similarity is 0 in case of
That is zero in case of
any words. Okay.
any words. Okay.
Okay, sir. Understood.
Okay, so this is the thing. Okay, so I hope this slide is clear to all of you. This is the base of this NLP. I hope this is clear to all of you. No doubt, right? Okay. Okay, so now we will be doing something called distributed representation of words. Earlier in the problem of one hot encoding was we are not finding the similarity, okay, but we always know that like this quote by Firth in the year 1957, it shows that you shall know a word by the company it keeps. Okay, that means we know that some words always appear to be together, like whenever we are whenever we are discussing this word bank, it always come with something called deposit, credit, etc. Okay, so that is what was the idea of this distributed representation of word, that you shall know a word by the company it keeps, means some word always appears with some other words. Okay, that is the thing. So distributional similarity based on this representation, and this leads to the idea of something called co-occurrence matrix. Okay, so what is this co-occurrence matrix? Now again, this is our corpus, and in this co-occurrence matrix what we do is we have two terms. Okay, one is word, and other one is context. Okay, so what is this word and context? The word and context comes from same thing, that is vocabulary set. Okay, the vocabulary set we have just seen. So this words and context will come from vocabulary set. Okay, words will be on the rows, and context will be on the columns. Okay, by that we will make a table. Now how we will put the value, that is a question. So for that, what we do is we take the window of words. Okay, window of words means how many terms we are interested in. Like we are interested only a window of k equals to 2. Now what we will see is, in the sentence we will be seeing only two words, like human we will see only two words after human. Okay, so human and machine, so if human is our word and machine is our context, so human and machine we will write one here, like this. Okay, so this is the word into context. Again I am repeating, word and context are the two terms that will be achieved from your vocabulary terms. So you will be achieving a corpus, and after achieving a corpus, what you will do, you will be dividing this corpus in a vocabulary set. Okay, and in this vocabulary set, all the words that you got in the vocabulary set, that will be assigned into two terms. One is word and the one is context. You will write the words in the rows, you will write the context in the columns. Okay, and then you will be seeing what is the window. Okay, window is how many words together we are interested in. Okay, so like window is 2, so we will be seeing only two words at a time. Okay, so here the window is 2, so we will be seeing only two words at a time. And then like human and machine, human is our this yeah, human is our word and machine is our context. Okay, so human and machine, in the intersection of the word human and context machine, we will write one. Similarly, we will be making our co-occurrence matrix. Okay, now what are the limitation of this co-occurrence matrix? One is something called stop words. Yeah, we are interested in finding the similarity between similarity, or seeing which of the two words will occur more often. But the problem is there are some stop words like for, the, etc. that will always that can always appear with any word. Okay, so these are the words that are known as stop words. So if we are having a large corpus, what we can see that the for this stop words or this for this stop words in the context, we will have many value like 100, 200, 300. So that is not important to us. So that is why first thing what we can do is we can solution one is ignore very frequent words. So wherever we are finding the words that are very frequently occurring, so these are actually stop words, so we can just ignore it. Second thing what we can do is, like two words are occurring always, the stop words, this is again a problem of stop words. What you can do is you can fix a threshold, like you can always fix a threshold, like this for an machine, like this value is 100. Okay, like this value is like 1000. Let's say this value is actually 1000, but you know it does not make sense because for can appear with machine. We are not interested in this stop word. So what you can do is you can give a threshold, like I am giving a threshold 10. So what this xij or this value of value here, what it will be your threshold. Okay, minimum value of your count or threshold. Okay, t is the threshold and this is the count. Our count was actually 1000. Okay, but I have given a threshold 10. Okay, so this this x will always be 10 in this case. So this is the second solution to fix the problem of this stop words. Okay, there are other solution. The other solution is something called PMI, okay, pointwise mutual information. Okay, so what is this PMI? PMI says that instead of doing all this xij, that means instead of just writing how many words will appear after how many context word is appearing after the word, what you will do, you will calculate something called this PMI or pointwise mutual information. Okay, so what you will do in this pointwise mutual information is, this is the formula. Okay, PC into, there will be PW also here, I will make the correction, there will be PW also here. Okay, PC by PC given W divided by PC into PW. So this is the formula of this pointwise mutual information. So instead of just writing, we are putting this pointwise mutual information. Okay, so what is this? This is the formula of this PMI. So earlier we are just writing how many context word is appearing after a word, but here now what we will do, we will be writing something called PMI. Okay, another thing what you can do is PMI. Whenever you will be doing this log term, what will happen is some of the words for some of the count WNC, wherever the count WNC or WNC word and context word appearing together, some value will be there for which the WNC will be 0. Okay, so to eliminate this, what you will do, whenever the count WNC will be 0, this term will be log of 0, and log of 0 will be minus infinity. So to counter this, we come with this PMI naught. So what is this PMI naught? In this PMI naught, what we will do this, we will always write PMI of this PMI whenever the word count is greater than 0. Whenever it will be equal to 0, we will be writing this 0 instead. Okay, so this table is of this PMI not PMI. Okay, because 0 is written, so that is why this table is of PMI not. And another thing what we can do is positive PMI. So positive PMI means whenever the PMI will be coming positive, then only we will be writing the PMI. In other ways, we will not be writing the PMI, or we will be assigning the PMI to 0. So this three solution we can use. What are the three solution? First is just ignore the stop words. Second solution is make a threshold. Instead of just writing whatever the xij is coming, what you will do is write a threshold of it. Like your for is appearing with machine 1000 number of time, you know this does not make any sense, so you just give a threshold, and you say that if the count is you just take the minimum of the count and threshold. Okay, if the threshold is less, you just take the threshold, otherwise you can take the count. This is the second solution. Third solution is something called PMI, or pointwise mutual information. So this is the formula of PMI. So instead of writing just xij, you just write the PMI. The problem with PMI is this log term. So whenever the log term will be there, whenever the value of count W and C is 0, your answer would be coming minus infinity. So to counter this, we have come out with this thing called PMI naught. In PMI naught, what we do is whenever the count of W and C is greater than 0, we write the PMI, otherwise we write it as 0. Similarly, this positive pointwise mutual information, whatever we do is, again for this log some value could come negative, so again that does not make sense. So that is why what we do, wherever the PMI is coming greater than 0, for that only we will write the PMI. For other cases, we will be writing the 0. So these are the three fixable solution of this stop word problem. What are the other limitation with this co-occurrence matrix or this distributed representation of words. Other problem is other problem which are non-fixable. First is again we have a very high dimensionality problem, because earlier in one-hot encoding also we have this dimensionality problem, because there can be so many words in the vocabulary. Okay, so that is why this is a problem. So this is again, this is a non-fixable problem. Second is the value is sparse. You can see in the table the value is appearing only for very sparse term, other values are all zero. Okay, so that is why this is a problem, because the things are very sparse. We have information, but this information is very sparse. The other places it is always empty. So that is again a non-fixable problem of this. Third is it grows with the size of vocabulary, same thing. So what is the solution? Solution is, whenever we have this high dimensionality solution, we go with dimensionality reduction technique. What are the dimensionality reduction technique? One is PCA, second is SVD. Okay, we have already discussed in this week 5 discussion. You can see the lectures. So yeah, two methods we can apply. One is PCA and one is SVD. Why we prefer SVD rather than PCA? Anyone can answer why we prefer SVD in place of PCA? Okay, where do we apply PCA and where do we apply SVD? Am I audible? Hello? Hello?
Sir, you are audible.
Okay, so can anyone answer it? Where we apply PCA and where we apply SVD? Both are dimensionality reduction technique, right? And both have this same procedure of decomposition. Okay, so why we eigen value decomposition and singular value decomposition, both have unique formula. Okay, means very similar formula. But where we use SVD, where we use PCA, we use PCA in places where we have square matrix. Okay, and we use PCA where we have square matrix. We use SVD where we have rectangular matrix. So it is we are not sure that whether this co-occurrence matrix can be a rectangular matrix or square matrix. That is why we will be using the SVD. Okay, so that is the thing. Again I am repeating, PCA we use only for square matrix, SVD we use for rectangular matrix. Okay, so we don't know in this problem of this co-occurrence matrix, like some cases can be there the words are more and context are less, so that will give us a rectangular matrix. So in that case we can only use SVD, we cannot use this PCA. So that is the thing. Okay, for this SVD, why we are using SVD in place of PCA. Okay, so our idea is to reduce the dimension. Okay, so this is our idea. So singular value decomposition, we all know how we write SVD. SVD we write something called this U, then this there is a sigma matrix, and then there is a V matrix. What is the order of U? U is something called M cross K. Okay, what is this sigma? That is K cross K. And what is this V? V is K cross N. Okay, this is the order of the all the three matrix of this SVD decomposition. Okay, so SVD or EVD or eigenvalue decomposition, what we do in this is we divide a full matrix into three matrices. Okay, one is U and there is sigma and there is V. Okay, in that PCA we tell it as V sigma and V inverse. Okay, that is the only difference. Okay, but same thing. So what we do in this singular value decomposition is in the sigma matrix we have all this singular values. Okay, what are the singular values? Singular values are square root of eigenvalue. Okay, so in this matrix we will have only singular value, and you know in eigenvalue decomposition that to reduce the dimension we take the dominant eigenvalues and we leave the rest eigenvalues. Similarly here also we can take the dominant singular values and we can leave the other singular values. Okay, so for example we require a k rank approximation, so for that we will take the first k of this singular values and we will leave the rest others. Okay, so that is the thing, that is how we can do the SVD. That means we are retaining only k singular value. We have n singular values, but we are only taking the top k singular values. We are not taking the other k minus n singular values. So by that we can do the dimensionality reduction, because as we are taking only the top k singular values, so we can do the dimensionality reduction. Okay, what will be our matrix? Our matrix will be positive this matrix. Okay, positive pointwise mutual information matrix. Okay, ppmi matrix. And in this ppmi matrix, what we will do, we will be doing the applying the SVD. Okay, applying the SVD to reduce the dimension. Okay, now what is the idea of doing that? Wherever we are doing this dimensionality reduction, what is our target? Our target is to retain the main information, and the information which are not important to us, we can just leave that or eliminate that information. We can only take the information that is very much important to us. That is the idea of this dimensionality reduction. So for example, you can see in this one hot encoding of this green color. So we have very light green, dark green, and very dark green. In all the green we have same information. Okay, but in this light, very light, we have this very light one is here. For this light, one is here, dark one is here, and very dark one is here, over here. But if you want only the most important information, that is green, we can just eliminate the other encoding part. Okay, because green is the most important thing that we are most interested in. We are not interested in whether it is a very light green, dark green, or very dark green. So that is the intuition of using the SVD. So by that, what we are doing, we are just reducing the dimensionality of the V. Earlier our V is of set 8, but now our V is of only set 4. So that is the intuition behind this SVD. Okay, so this is the thing. Now whenever we are doing just ppmi, you can see this is the co-occurrence matrix, and this is the thing. Now in this co-occurrence matrix, one of the most important thing is, you can see this system and machine. Okay, the system and machine, we are getting the value 0. That means system and machine are not occurring together in our corpus. But that is not the case. Okay, we know that is not the case. Whenever you will be applying a big corpus, this system and machine must be related somewhat. Okay, so what does SVD do is, whenever we are converting this X matrix to a lower rank matrix by applying this SVD, what you can see, this system and machines is now related by 0.23. Okay, so that is the thing. So notice that after low rank reconstruction with SVD, the latent co-occurrence between the system and machine and human and user has become visible. Earlier it was 0, but now it has become visible. Okay, so this is another advantage of applying this SVD. Okay, and the advantage what you can see with the help of this cosine similarity that I have discussed in the first slide only. So cosine similarity, how you can find the cosine similarity? You can, if you have this matrix, you can find the cosine similarity of this matrix by x dot xt. Okay, so transpose of this matrix, and whenever you will be do the value that is coming here, that are the cosine similarity of the word and the context term. Okay, so these are all the cosine similarity. Now when you have applied this SVD, now what is the thing? Previously this is the cosine similarity, but now after this lower rank, okay, earlier our matrix is x, now our matrix is x x bar. Okay, so x bar, whenever we are taking the cosine similarity of x bar, you can see earlier the human and user cosine similarity was it was 7.01, and human and user. Okay, human user, So yeah, there is some cosines of, yeah, so this is only this top term, okay, x dot xt, but you will be again dividing by x bar and xt bar. Okay, so cosine similarity earlier was 0.21, but now you can see the cosine similarity has increased to 0.33. So this is the advantage of applying the SVD. Okay, in SVD what you do, you for this word matrix you only take the first two term, that is u and sigma. Okay, and this word context you take the v term. Okay, so this is again maths. I am not going deep into maths. You just understand this thing, that yeah, whenever we have applied this SVD and make this co-occurrence matrix to a lower rank matrix, what we can see, uh, our our values are visible in case of system and machine, and human and user. Earlier it was 0, but now it was visible. In terms of cosine similarity, earlier the cosine similarity was smaller, but whenever we have applied this SVD, the cosine similarity also increases. Okay, so what we are doing, the words that are similar or will occur more often, we are decreasing the distance between the two words. So that we are doing by SVD, by uh, by uh, projecting our vectors into a new basis. Okay, so that is what we are doing by this SVD. Okay, so this is the thing. So is it clear? At least you got some intuition. uh, I hope at least you have got some intuition. Okay, one day it is not possible to learn this SVD or SVD on this NLP, but at least you got some intuition why we are doing this, etc. Okay, so I hope it is clear, somewhat clear, I hope. Clear, right? Am I audible? Am I audible?
Yes, sir, yes, sir, yes, sir. Yeah,
Okay,
audible.
okay. So let's
Yes,
move,
sir.
yeah, let's move on to the next thing, that is count based versus prediction based model. So whatever the thing that we are seeing by this co-occurrence matrix, all these models are known as count based models. Okay, now what is this count based model? The method that we have seen so far are count based model, because they use this co-occurrence count of words, means how much two words are coming together. Okay, that they are measuring. So these models are known as count based models. So we have this other model known as predict based model or prediction based model. So we will now see methods which directly learn word representation, and these are known as prediction based model. So again I am repeating, there are two type of model. One is count based model, and the thing is prediction based model. What are the count based model? Count based model only count the number of co-occurrence of words that is coming in the co-occurrence matrix. Now what we will see something called predict based model. Predict based model, what it will do, like we have four words, it will predict what is the fifth word. Earlier what we are doing in the count based model, like two words are there, we are seeing how much these two words are coming together. Now what we will do, we have four words and we will predict the fifth word, like that. So these are predict based model. So this we will see. So this we will see. Okay, so this is the prediction based model working. You can see here we have a window of 5 words. Okay, this is a window of 5 words. We are interested. What we will see, we will take the n minus 1 word, that is the 4 words we will take, and we will try to predict the fifth word. Okay, similarly here also we are taking the 4 words, and we are we want to predict the fifth word, like that we will do this. So that is how a prediction based model works. Okay, so first prediction based model is this something known as continuous bag of word model. Yeah, for this prediction based model we need to predict our output. So for that we will be doing our deep learning. Okay, or we will be applying our deep learning for this predict based model. Okay, so the first model is known as continuous bag of word model. What does continuous bag of word model, what is its input? Input is one hot representation of context word. Okay, so the input is one hot representation of context word. And what is your output? Output is output, there are v words classes possible that we want to predict a probability distribution over this v classes. Yeah, so actually, yeah, so you have two things that we have already discussed in this. Okay, someone is joining, that we have already discussed in this co-occurrence matrix. One is word, second one is context. So what does this continuous bag of word model does is it's take the input as the context and it will predict the output as word. Okay, so we have two things, one is word and another one is context. What is input of this continuous bag of word model? That is context. Okay, okay, so let me, yeah, the input is this context. Okay, and output is the words. Okay, like there is this one hot representation of this word sat. Okay, sat is a context word. Now what you are interested in, you are interested to find a word that will be after the sat. So we are taking the window of k equals to 2 only. Okay, k equals to 1 only, sorry, k equals to 1 only. Okay, because here we what we are interested after one word is in the context and we want to we want to predict the word that will be predict the word as a output. Okay, so sat is our context word. We want to predict what is the probability that on will come after sat. On will come provided sat is the context word. So this we are interested in. Okay, so this is the thing. So like what we will do, we will make this as a neural network model. In the neural network model, what are the parameters? Parameters are the weights in the this context word and this words w words. These are the parameters we have. And what are the two things that are important? One is the output function that we are using, as this is a classification problem. Okay, because we have so many classes. What are the classes? Like what is the probability that he will come provided sat is there? What is the probability that chair will come provided sat is there? What is the probability that man will come provided sat is there? So these are the classes we have: he, chair, man, on, etc, etc. These are the classes. Okay, and what is the input? Input is the sat. Okay, so this is the thing. Now whenever we have this classification problem, the output function that we are using is softmax function. So this is the formula of the softmax function. Okay, and what is the loss that we use? We use a loss known as cross entropy loss. So the cross entropy loss we will be using, and we will be using the output function as a softmax function. That also we have learned in the second or third lecture, that wherever there will be a classification problem, the output function is always softmax function, and the loss function is a cross entropy function. Okay, so that is what we are using. And what we will do, we will train our neural network. We will our weights will be learned, this w word and w context. These are the weights that will be learned, and by that what our target is to maximize this probability. Okay, so that is our target. So this model is known as continuous bag of word model. So again I am repeating, what are the major things that you have to understand. I am not going much into maths and all, you can see in the lecture notes. But what are the major things that you have to understand? First major thing you have to understand, what is this continuous this is a prediction based model. What is a prediction based model? Prediction based model means you will be given some words, you have to predict the word that will be coming after the given set of words. So that is a prediction based model. Okay, now there are two terms that we have already discussed. One is the word term and the one is the context term. What the continuous bag of word model does is we have this context term, now we have to predict the word term. Okay, so in this example we have a one context term, that is sat. Okay, and we have to predict what will be the word that will be coming after this sat. Okay, so we can have many classes like he, chair, man, etc, on, etc. So we have to do what we have to do, we have to see the probability probability of each that will be coming, and the probability will be coming maximum for this on word, because we all know that after sat there will be on coming, sat on chair, sat on bench, etc., etc. Okay, sat on ground, like that. So after sat we always get this word on. So for that, so we are modeling our neural network like that only. And what are the input is this context word set. And what is the output we have so many output, and we want to maximize this probability of on provided set. Okay, so what is the function that will be using on the output? The function we will be the activation function that we will be using on the output layer, or the output function we will be using is softmax function. And what is the loss function will be loss function will be using? Loss function is cross entropy, because this is a classification problem. Okay, now what are the limitation of this continuous bag of words? One, that we are using the softmax function, and this is very expensive. Okay, because we have so many words or the full vocabulary in the output. From that we have to predict what is the most suitable term. Okay, for that we have to do so many calculations, like we have to calculate the probability of this class, probability of this class, and we have to take the probability of all the class. So that is why this softmax function is computationally very expensive. Okay, and for even for finding probability of one class, in the top we will have this word, means the word that I is the word that we are interested, and this is the whole weight that is coming. But in the denominator always we have this bunch of words. Okay, so that is the problem, because in the denominator we will have the words that does not give us maximum probability, also that words will also come in the denominator part. Okay, so that is why this softmax function is computationally very expensive. So that is the major limitation of this continuous bag of word model. Okay, so is this thing clear, at least some part of it? Is this thing clear? Am I audible? Okay. Okay. So let's move on to the second model. Second model is a skip-gram model. So earlier what we have seen, we have given the context and we will be predicting the word. Here is the reverse case of the continuous bag of words. Here we will be providing words as the input, and we will try to predict the context words as the output. Okay, so again I am telling, in the continuous bag of word model, CBOW model, what is our input? Input is our context, and output is our word. Okay, here in this skip-gram model or SG model, here the input is our word. Okay, and output is our context. Okay, this is the only difference between the skip-gram model and the this continuous bag of word model. Okay, now another thing, as we are predicting the context term, the context can be context is always greater than words. Okay, so like like here we are giving some kind of word, the context can be a set of all the words. So here our loss function is always again greater than this continuous bag of word model, because we have to keep on adding the terms. Okay, earlier we have only we are focused on only one loss, but here we have to do this for all the context term that can appear. So our this output is a major headache here. So because here the loss function will take all the terms, like this loss function will also take this term, plus loss function will take this term, plus loss function will take this term, and all the terms, because here we have a word and we have to find the context. Okay, so that is why we have a much greater loss function. Okay, this is the problem. Again, we will be calculating our output with the softmax function. Again, this is computationally expensive. So to deal with this, we have three methods that we use. Here our loss function is the major limitation, right? So what we will do, we will be applying three methods so that our loss function will be smaller than this loss function. So what is the first method? First method is something called negative sampling. Okay, so what we do in negative sampling, we make this two type of pair. One is this correct pair, like what are the words and words can appear together, that is the correct pair. And what we do is incorrect pair, like these are the correct pair, means sat and on can come together, sat and chair can come together, on and chair can come together, a chair can come together. These are correct pairs, so correct word context pair. Okay, now we have this incorrect word context pair, or pair, that is WR, like sat and oxygen. Sat and oxygen will not come together. Sat and magic might not come together. Chair and sat might not come together. Chair and walking might not come together. Okay, so these are the two set that we prepare. One is the set of correct words and context pair, and second is incorrect word context pair. Okay, that two sets we make. Now what we will do, we will what our target is to maximize this term, that is the correct pair, and our target is to minimize this term, that is the incorrect pair. We know the probability will be 1 in case of word and correct pair, and probability will be 0 in case of word and incorrect pair. Okay, so what our target, we will be maximizing both this probabilities. Okay, one is the probability of word and correct word pair, and the probability which will be 0 in case of incorrect word pair. Okay, so these two things we will be multiplying and will be minimizing. So by this we will be limiting our loss function. Earlier our loss function was very large, but now we have introduced this new loss function. So by this new loss function, our computation type will be very much smaller than what we have seen. So this trick is known as negative sampling. What is the next trick? Next trick is something known as contrastive estimation. Again, same type of thing. Contrastive estimation means the estimation, contrast is something opposite, right? Earlier we have this positive statement that he sat on a chair. Now we introduce a negative statement, he sat abracadabra on a chair. Okay, so we know this on is correct and this abracadabra is false. So the output here is coming something called S, and the output here is coming SC. So what our target, we will be formulating our loss function such that our S minus SC we have to maximize. Okay, now there is a S is the correct thing and SC is the incorrect thing. So S minus SC I have to maximize. Okay, in order the neural network to learn. Okay, now the thing is how much the S is greater than SC, means what should be the difference. So for that what we do is we introduce a term called M, and we say that this S should be greater than SC with some term M. Okay, so that we introduce, and what we do, what we our loss function now will be, it will be maximum of 0 or this S minus SC plus M. That will be a loss function. Again, previously we have our loss function was so large, and now we are decreasing our loss function to this. So this is known as contrastive estimation. What is the third thing that we do? Third thing that we do is something called hierarchical softmax. Hierarchical softmax, what we do, we construct this binary tree. Okay, so we have two nodes, one is the leaf node and one is the root node. Okay, the top node is always called as that exists the unique part from the root node to the leaf node. So top node is always called the root node, and the node which we are interested to reach, that node is called the leaf node. So now what we have to do, for each correct word, whenever we will be moving towards the correct word, for that path the probability will be 1, and for each incorrect path the probability will be 0. For example, this is our root node and this is the leaf node. So for this, whenever we will be traveling the left node, our probability will be 1, and otherwise our probability will be 0. So like that. So what you will do is, for each probability you will be forming the loss function, and you will be multiplying the probabilities. Okay, so what is our target? Our target is to maximize the probability, or maximize the correct path to reach our destination, or reach the leaf node. Okay, so that is the thing. Okay, so this is known as hierarchical softmax. So all these tricks, I am not getting more into maths and all this trick. Why we are doing this? Earlier our loss function is very large, okay, and loss function is a headache. Now all these three things that we have done, negative sampling, contrastive estimation, or hierarchical softmax, we have reduced the loss function to a much smaller function. So that is the idea behind this introducing these three things, that is negative sampling, contrastive estimation, and hierarchical softmax. Earlier a loss function was a major problem. Now we have get rid of the loss function. We are doing all this negative sampling, contrastive estimation, or this hierarchical softmax. So this is the concept. Okay, so this is the thing. So is the concept clear why we are doing this? At least the concept should be clear why we are doing this. Earlier we have this so large loss function. Now by applying these three methods, we are reducing a loss function to a much smaller value. That idea should be clear at least. Okay. Now let's move on to the next thing, that is glove representation. So we have seen two type of things. One is the count based prediction method, count based methods, or count based model. Second is the prediction based model. Now in the glove representation, our idea is to combine this count based model and prediction based model. Okay, so the count based methods or the SVD, it rely on global co-occurrence count from the corpus for computing word representation. Predict based method learn word representation using the co-occurrence information. So our glove representation, why not combine both the thing, that is count based method and the predict based method. So if we combine the count based and method and predict based method, we came with this new idea known as glove representation. This is not that glove, this is global vector. Okay, glove is the short form of global vector representation. Okay, so again I am telling, we have learned the count based method, that is SVD. Whenever we are applying SVD on a co-occurrence matrix, what we are learning how many times two words are appearing together, two words or a set of words are appearing together. So that we are doing in the count based method. What we are doing in this predict based method, what we are doing is, we are given a set of words. We are interested to learn the next word. What will be the next word that will be coming after the given set of word, that we are interested. So when we are just merging both the two, that is count based method and predict based method, we are arriving to this model known as glove model or glove representation. Okay, glove is the short form of global vector. Okay, so again I am not going much into maths, but see, this is the co-occurrence matrix, and this Xij is nothing but your ppmi. Okay, that is how much this two words are coming together, something like that. Okay, so that is your this that is your count based method. Okay, now what is the predict based method? Predict based method is, if we are giving two set of words, how much similar they are. So something like that we find in this predict based method. So this is our idea of the formula. So yeah, this is our total formula. So see, we have two part. One part is this part, that is logs xij. So this depends on the actual value computed from the given corpus, and this is the value that is predicted value based predicted value using the model parameters. Okay, so this portion is the predicted, this portion is the actual, and we always know that what is MSE or mean squared error, that is y predicted minus y actual and the whole square of it. Okay, so same thing. So we have predicted in one set that we will be achieving from our predict based model, and we have this actual thing that is on the other side that will be achieving from our SVD or count based model. If we combine these two and we minimize the loss, we will be getting our glove representation. So this is the idea. Okay, again I am not going much into this maths and all, but this is the idea. Like we have two model, one is this predict based model and one is this count based model. So we have this something loss function for this predict based model, we have this something loss function for this count based model. So if we can subtract both this and minimize the loss, we can get our loss function for this glove representation. So this is the idea of this glove representation, okay, or global vector representation. Okay, so is the idea clear? At least the idea should be clear, that we have two things, one is the count based model, one is the predict based model, and now we are doing this. Okay, and then we have this something called evaluating word representation. So how do we evaluate? Yeah, we have now formed our model. Now how we can evaluate our model? So we can evaluate our model based on three tasks. One is semantic relatedness. So what does semantic relatedness means? Semantic is something related to meaning of words, that is semantic. Okay, like the cat and dog. Okay, so what is the cosine, what is the similarity that our model is predicting? Cat and dog, that is 0.7. And what we will do here is we will also take the help of human. So how the human is, what this human is, we will take the sample information from different human, and what we will say is you decide that how much the cat and dog is similar. So we have this similarity based on human, that is 0.8. We have this similarity based on model, that is 0.7. Now how we can say that which model is better than which model? In case of this semantic relatedness, how we can say? We can do the correlation. Okay, correlation of the human and the model, whatever. Okay, the model. Okay, now if the correlation of model 1 with respect to human is greater than correlation of model 2 with respect to human, we can say that model 1 is performing better than model 2 in the case of semantic relatedness. So again I am telling how we can evaluate the model. We have already made the model. Now our idea is how can evaluate the model. So the first task to evaluate the model is semantic relatedness. What is semantic? Semantic is something related to meaning. Like we know the cat and dog are animals. Okay, so this cat and dog must be similar in some case, some kind. Okay, so we will tell our model to decide how much the cat and dog are similar. So that is coming 0.7. But just taking the output of a model is not good. So what for that what we will do, we will also take the help of human. Okay, we will take a sample size and we will ask the human how much you think that the cat and dog are similar. So they will give some value, and then we will take the correlation of this human and model. And for which model the correlation of the model and human will be greater than if the model 1 has more correlation, if the this model 1 has more correlation than model 2, then we will say that model 1 is better, performing better for semantic relatedness than this model 2. Okay, now this is our second task. What is our second task? Second task is something known as synonym detection. Okay, synonym, you all know, the words which have same meaning are known as synonyms. Okay, so we have this term and we have this candidate. What is our target? Our target is to target, or this is the function or loss function. Our target is to maximize the cosine similarity between this term and this candidate term. Okay, that is our target. So which model will be performing well, we can find out by this. Okay, so this is the second task for which we can judge our model or evaluate our model. What is the third task? Third task is something called analogy. Now this analogy can be of two types. One is the semantic analogy, and the other is syntactic analogy. Semantic analogy means analogy, you all know, like brother is related to sister, then grandson is related to what. Okay, so for that we will be using a semantic analogy, because here we know that brother and sister are related by something. That brother, sister is the feminine gender of brother. Similarly, what should be the feminine gender of this grandson? So this type of analogy, wherever we are doing the analogy based on meaning, okay, this type of analogy is known as semantic analogy. This another type of, okay, someone is joining. Okay, another type of analogy known as syntactic analogy. Syntactic analogy means, syntactic means how is the word or letters are arranged. Okay, that analogy we are, by that analogy we will judge our model or evaluate our model. Like work is related to works, what is speak related to? So speak will be related to speaks, right? Because s is added in this, so s will be added to our this word. Okay, so speaks. So this is syntactic. Here we are only here we have what we have seen, we have only seen what is the arrangement of the letter in the word. So that is syntactic. We are not interested in meaning, but we are interested in what is the arrangement of the letter in the words. So by that also we can evaluate our model. This is three tasks for which we can evaluate our model. One is this semantic relatedness, second one is this synonym detection, and third one is this analogy. Okay, by these three tasks we can evaluate our models. Okay, so that is the thing. So
So
it
how
is
you got point 0.8, sir? Point 0.8, point 0.7.
0.8, 0.7. So this is yeah, this the model is only given because this cat and dog will have some vector, the one hot encoding, like that. Any type of encoding will be done by the model, and the model will be achieving this 0.7. 0.8, it is related to asking human, like you will be collecting data of many human, and you will be seeing that how much you just like you will be asking that rate out of 1 to 10, how much similar you will rate cat and dog. So some will say 7, some will say 9, some will say 10, not 10, 9, 9.5, etc. You will take the average and you will be achieving this. Okay, similarity of human. Okay, is it clear? It is some case of sampling only. Okay,
Yes,
sampling
sir.
based on some thing. So this is the thing. So this is how you will evaluate the model. These are the three tasks: semantic relatedness, synonym detection, and analogy. So this is the thing. So I hope this is clear to all of you. Now we will move on to the last thing, that is count versus prediction model. Which one is better? Okay. So there are many studies. Some say that count based model is good. Some say predict based model is good. So this was a study by Boroni and others in the year 2014. And what they have shown that predict based model consistently outperform the count based model. And then there was a study by Levy and others in the year 2015. They have done a more thorough analysis than this Boroni and others. What they have done, they have shown in their result is prediction based model will be is working better on similarity tasks but not on analogy tasks. Okay, so prediction based model will work better for similarity tasks, but it does not work better on this sorry, not prediction, SVD does better for this similarity task, but SVD or the count based models will not done well for this analogy task. Okay, the Levy and others, they have given this results in their study. Okay, in the year 2015. Now what is the relation between SVD and word vector? Both this we are dealing with the word context and word W word. Okay, both this we are dealing with the word context as well as W word vectors. So that is why there is some kind of similarity. Also in the SVD you have seen that we are making this co-occurrence matrix, and we are taking the word vector in the rows, and column vector context vector in the columns. Also in case of this predict based model, either in this count based continuous bag of word model or the skipgram model, we are again dealing with this w word and w context only, right? So that is why you can say there is a relation between the SVD and word to vec. Word to vec is nothing but the prediction model, that is continuous bag of words, and the skipgram model, okay, that is word to vec model, okay. So that is why we have this relationship between the SVD and word to vector model. Both these cases we want this w context and w words, okay. So that is why they have some relations. So that is what the Levy and others shown in their study in 2015. Okay, so this is just a informative slide. You can just read it. This is not so important. Okay, so this is the thing. So any doubt in today's lecture? Anywhere you can ask. Anywhere you have a doubt. I know the maths and all this is a tricky part, so just ignore the maths and all. I hope the theory is clear to all of you. What we have discussed the one hot representation of word, okay. Then what we have discussed the distributed representation of word. Here we have discussed something called co-occurrence matrix. Then from this co-occurrence matrix, the problem in both this thing was the size of the vocabulary, because size of vocabulary can be so large whenever we are dealing with large documents like Google dataset, etc. There the size of vocabulary is very large. So to reduce the dimension, we have done this SVD, okay. So after SVD, this all are something called count based method. Here what we are doing is we are seeing how much the two words or the group of words are appearing frequently, that we are checking. So that is SVD, that is the count based methods. After that, what we have done this something called word to vector models, that is the predict based models. Okay, predict based model, what we are doing, we are giving a set of words, and now we are interested in predicting the word that will come after this set of words. So that is the predict based models. There are two models. One is this continuous bag of word model, and second one is skipgram model. Continuous bag of word, what we are doing, we are doing the we have this context word, we are supplying the context word as input, and the output we are getting the word, okay. And skipgram model is the opposite of it. We are supplying word as the input, and we are interested to find out we are interested in output, what is the context word that can come after the word. So that is the skipgram model. Now what is the glove representation? The combination of the count based model and prediction based model is the glove representation or global vector representation. And then we have seen some of the things related to count based versus prediction based model according to the study by the Levy et al, Levy and others, and this Boroni and others. Okay, so this is the thing. Okay, so I hope some theory is clear to all of you. At least you got the idea. This NLP is again a very vast domain, but at least you get the terms, you get the idea. That should be clear to all of you. Okay. So by this we will be doing our this question answers, okay. So this is the first question. Again I will request everyone to guess the answer first, and then we will discuss the answer, okay. So consider the following corpus: human-machine interface for computer applications, user opinion of computer system response time, user interface management system, system engineering for improved response time. What is the size of vocabulary of the above corpus? So any guesses for this? Size of vocabulary, what will be the size of vocabulary? Any guesses for this?
16.
16, okay. 16. Okay, so let's see. So what you will be do? What are the steps you will be doing? First, you will tokenize or split the sentences into words. That is known as tokenization, okay, or split the sentence into words. So you will just these are the four sentences. You have this first sentence, you have this second sentence, you have this third sentence, and you have this 4 sentence. Okay, so we have 4 sentence. What we will do the tokenization or split into words. Okay, so we will just split it. So human machine interface for computer application, user opinion of computer system, response time, user interface management system, system engineering for improved response time. So we have just do the tokenization or split the sentence into words. So that is our first step. Second step, whenever we will be doing we are interested in the size of vocabulary, the vocabulary will always consist of unique words. So we have to make sure that we are not repeating the words in the vocabulary. So what will be the vocabulary? This will be the vocabulary. Okay, here these are the this row. What I have done is, this row I have written all the repeated words. Okay, so this repeated word we should not use this repeated word in the vocabulary. Okay, because user is always already coming, computer is also coming, interface is also coming, system is coming, again system is coming, for is coming. Okay, response is coming, and time is also coming. Okay, so this words has already came once. Okay, so what is our idea? Our idea is to avoid repetition of word in the vocabulary. Okay, the vocabulary is always formed by unique words. So now we have to find out what is the size of vocabulary. So just we have to count the words in the vocabulary. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So 15 number of words are the unique words in the vocabulary. So 15 is the size of the vocabulary. Okay, so C is the answer. Is it clear to all of you? What is tokenization? Tokenization is splitting the sentences into words. After we do the tokenization, we have to write the vocabulary. Okay, vocabulary we have to avoid repetition of the words. We have to write unique words only. So whenever we have written the vocabulary, just count the number of words in the vocabulary, and that is coming 15. So option C is our answer. Okay, I hope it is clear to all of you. Now this is the question. Suppose that we use continuous back of words CBOW model to find the vector representation of words. Suppose further we use the context window size of 3. Given the 3 context words, predict the target word. The size of the word vector representation of word is chosen to be 100. Okay, size of the word vector is 100. Okay, so that means output we will have 100 output. Okay, 100 as output. And the vocabulary contains 10,000 words. So context is 10,000. Okay, so 10,000 is our context and 100 is our words. So the input to the network is the onehot encoding. Okay, how many parameters or weight including bias or excluding bias? Okay, excluding bias are there in the W word. Enter the answer in thousands. For example, if your answer is 50,000, you just enter 50. Okay, so that is nothing, just ignore this. This is the thing. So 2 things are given here. One is the words and one is the context. Okay, so context we have 10,000 word in our context and we have 100 word in our words. Okay, so what we do in continuous back of word model? Continuous back of word model, we have the context word, we are interested to find the words. Okay, so that is our targets. Now here it has been asked how many parameters are there in the W word. Okay, so let's just see the diagram, it will be more clear. So where is the model? Yeah, this is our model. Okay, so you will have this row and you have this row. Okay, this is the onehot encoding. Okay, so what you are interested to find the number of parameter in this area. Okay, so this area, this consists of, this is the context. Okay, this is the context and this is the word. So you have 100 word and you have 10,000. 1 2 3 4 10,000. Okay, 10,000 as the context words and 100 as the words. Okay, now you are interested to find the number of parameters. So number of parameter, how you can find? Just multiply 100 with that context word and that will be the number of parameters. So number of parameter is 100 into 10,000. Okay, and here you have been asked to give your value in terms of enter the yeah, in terms of thousand, so just divide by 1000. Okay, so this is the thing. Vocabulary size is 10,000, word vector size is 100. Whenever you will be finding the w word, your rows will be the vocabulary size. Okay, rows will be the vocabulary size, columns will be the word vector, and by that whenever you will be multiplying it, you will be getting this number of parameter, that is this that is 10,000 into 100 parameter, and divide by 100, because here it has been told to get the answer in terms of 1000, divide by 1000. So just divide by 1000, divide this by 1000, 1 2 3 4 1, this, so your answer will be coming 1000. Okay, so 1000 will be your answer. So is this clear to all of you? Okay, clear, right? Okay, so let's move on to the next question. You are given one hot representation of two words. One is car, one is bus. Okay, what is the Euclidean distance between car and bus? This is very easy. I hope everyone know what is the Euclidean distance between two words of the same vocabulary. This we have already discussed, right? In the first
1.414. Root 2. Root 2.
Yeah, root
1.414.
yeah, root 2. So very easy. You just do the Euclidean distance, that is ai minus bi. I is the position. Okay, let's say this is the a vector and this is the b vector. I is the position. This is the first position, second position, third position, fourth position, and fifth position. So you have to do this for all the position. First do for first position, then plus second position, third position, fourth position, and fifth position. Okay, so this will be coming, one will be coming for first position and one will be coming for fourth position. Okay, other will be 0. So it will be 1 plus 0 plus 0 plus 0 plus 1 plus 0 and root over of that. So that will be root over 2. So root 2 will be your answer. Okay, so this root 2 will be your answer, or the answer is this is a range question, so answer will be between 1.41 to 1.42, because root 2 is 1.414. Okay, so that is the thing. So I hope this is very easy to all of you. Let's move on to the next question. Let count WC be the number of times the word W and C appear together in the corpus, that is occur within a window of few words around each other. Further, let count W and count C be the total number of times the word W and C appear in the corpus respectively. Let n be the total number of words in the corpus. The PMI between W and C is given by option A is this, option B is this, option C is this. So any guesses for this?
C.
Yeah, C. Okay. So how you can find this? This is actually the formula of PMI. So PMI is this pointwise mutual information. Okay. So the formula of PMI is this, log PWC by PW into PC. Okay, this is the formula. How you can find PWC? Probability of W comma C will be found by this, that is count of WC divided by total number of words, that is count of WC by n. How you can find probability of W? Count of W divided by n. How you can find probability of C? That is count of C divided by n. You put all the three equation in this, and you will be getting your answer. So what will be your answer? The n and n will be cut, and this n will go there. So your answer will be count WC into n divided by log of count WC into n divided by this count W into C. Okay, so this is the thing. So option C is your right answer. Okay, so I hope this is clear. This is the main formula, and this is how you can calculate probability of W comma C, probability of W, and probability of C. Just put all this in this equation and you will be getting this. So C is the answer. Okay, so this is a theory question. This, if you know the theory, what is the formula of PMI, you can answer. Okay, clear, right? Is this clear? Am I audible? Now question number 5, which of the following is the advantage of CBOW or continuous bag of word model compared to skipgram model? It is faster to train, it requires less memory, it performs better on rare words. Option D, all of the above. So any guesses for this? Any guesses for this? No guesses? Okay, so what is the difference between CBOW model and skipgram model?
Context to word is CBOW model,
Yeah.
and word to context is skipgram model.
Yeah, absolutely. So, which should be smaller in the output? If I just focus on the output layer, which should be which model will occupy more memory in the output layer, whether it is CBOW or skipgram?
More
Skipgram,
memory will be
yeah, skipgram will
CBOW.
occupy more memory, right? Because here we are interested in finding the context. Okay, a word can have many contexts. Okay, but a context will have only one word, like that you can imagine. Okay, so that is why as the memory consumption of this skipgram is more than CBW, so it is faster to train. CBOW is faster to train. It requires less memory. Perform better on rare word, that we cannot say. So option A and B is the correct answer according to me. Okay, because this is the thing, CBOW predicts a single word using a multiple context of word, meaning it performs fewer updates per word pair compared to skipgram. Requires less memory since CBOW compute only one prediction pertaining example. It requires fewer parameter and less memory. Okay, so option A as well as option B are the correct answer. Option C, we cannot see anything about option C, so that is why A and B are the right answer. Okay, so is this clear?
So,
now again, which of the following is the disadvantage of one-hot encoding? Okay, so option A, it requires a large amount of memory to store the vectors. It can result in a high dimensional sparse representation. It cannot capture the semantic similarity between the words. Option D, all of the above. So any
all
guesses
of
for
the
this?
all of the
Yeah,
all of the
absolutely, all of them, right? Because we have already seen that whenever we are doing one hot encoding, it requires a large number of memory, because a vector size can be so large. So that is why it requires large number of memory. It can result in high dimensional sparse representation. Sparse representation means one can be here for 0 and 0 in all other cases, and there can be a word here, one here, and all other 0. So this 1 and 1 are, means zeros are more. Okay, and the information that we want is less. So that is why this suffer high dimensional sparse representation. Option C, option C, it cannot capture the semantic similarity of words. Yeah, cosine similarity in case of all this vectors is 0. Okay, because we know cosine similarity is the dot product of the two vector at the numerator, and for any two encoding, whenever we will do the dot product, the result will always come 0. So it cannot capture the semantic similarity between the words. So option D, all of the above, is the correct answer. Okay, so this is the thing. So all this are thing, you can read it, but this is the thing that I have told you. So option D is the right answer. Okay, so let's move on to the next question. Which of the following is an advantage of using the skipgram method over the bag of word approach? So option A, the skipgram method is faster to train. Option B, the skipgram method performs better on rare words. Option C, the bag of word approach is more accurate. Option D, the bag of word approach is better for short text. Any guesses for this? Okay, so no guesses. So yeah, so there can be two things that can be told for this. The bag of word approach is better for short text because bag of word approach, what we do in bag of approach word approaches, it does well for short text where a deep contextual embedding might not be necessary. Okay, because bag of word model, whenever we are talking about bag of word model, so we are interested in predicting only a single word. Okay, so that is why it works better on the short text, whereas skipgram model, it has so many context word in the output layer, so that is why it perform better for rare words. So this is the logic. Okay, now again it can be more or less confusing, but this is the logic. As skipgram model, it predicts so many context word in the output layer, so it is better for rare words, whereas this bag of word approach, it predicts only one word in the output layer, so it is better for short text. So this is how you can explain. So option B as well as option D is the correct answer. Option A cannot be correct because we all know that the CBOW model is better than this skipgram model, or faster to CBOW model is faster to train than this skipgram model. And option C, the bag of word approach, is more accurate. This is also we cannot say anything. Okay, so option B as well as option D is the correct answer. Okay, this is the thing. So this is the thing. This is again, you can say some confusion can be there, but these two are the appropriate options. Okay, this is the thing. So let's move on to the next question. Suppose we are learning the representation of words using the glove representation or global vector representation. If we observe that cosine similarity between two representation vi and vj for the words I and j is very high, which of the following statement is true? So for that, what you need to do, you need to know the loss function. Okay, loss function, or you need to know this. Okay, so in glove representation we have two side of the formula. One is this count base side, and the one is this predict base side. Okay, so the count base side only work with this xij, as the predict base side, it does the dot product of the word vectors, and it also take the bias terms. So that is the predict base side. Okay, so this formula you have to keep in mind. Now what has been asked, if we observe that cosine similarity between the two representation vi and vj for word I and j is very high. So cosine similarity in this formula, where can we use cosine similarity? We will use cosine similarity for this term. Okay, vi transpose into vj. Okay, this is where we use cosine similarity, because here we are using the dot product, and cosine similarity at the top we are doing the dot product, and at the denominator we have this magnitude of the vectors. Okay, so here it has been told the cosine similarity is high. Second thing, it has been told the value of bias is very low, that is 0.02 and 0.05. Okay, so what we can say for this xij? Now this term is high, and these two terms are also positive, that is 0.02 and 0.05. So our xij should always also be high. Okay, so xij should also be high. Okay, either you can no, vi transport and vj is not given. It just it is just saying that the dot product is high. Okay, dot product or the cosine similarity is high, that is all this is showing. So this value, this right hand side value is will be large. So when the right hand side value will be large, the right hand side value will be large when log of xij is large. Okay, and when the log of xij is large, when xij will be large. So what you have to do, you have to see which xij is maximum out of this four option. So maximum is B. Okay, so B is the right answer. This cannot be right, because xij, if you put xij as 0, the answer will be coming minus infinity, so this cannot be high. And this is also will be very closer to minus infinity. This is also not correct. So your option can be between B and C, but here we have been told that we have to take the value maximum. So maximum of 0.8 and 0.35 is 0.8. So option B is the right answer. Okay, so this formula you have to keep in mind to solve this question. Okay, so this is the thing. So xij 0.8 is the highest among the given values. Okay, so that is why you can just take the xij equals to 0.8 as the correct answer, or the B as the correct answer. Okay, so this is the thing. So is it clear to all of you? Okay. So question number 9, what is the computational complexity of computing the softmax function in the output layer of the neural network? On square, On log n, or O log n? So any guesses for this? Yeah, Shyam, if only one to select, what is the correct answer? Shyam, you are asking for which question? Question number 8? Are you asking for question number 8? Shyam? Am I audible? Are you asking for question number 8? Okay, 7, okay. Okay, let's see the question number 7. Okay, the skipgram, yeah, so yeah, both these are correct according to me. Okay, so most appropriate, you can say the skipgram model performs better on rare words. This is more appropriate. This is partially true. Okay, partially true, you can say. According to the question, it is true, because here we are only seeing this context word, and we are only seeing on the basis of the output layer. Okay, so that is why B and D is correct for this question. But more appropriate, you can say B is more accurate. The skipgram model method performs better on rare words, because we are finding the context of the words. Okay, so that is why skipgram performs better for rare words. Short text we cannot say very accurately whenever we are talking about short text, but with that logic we can say it is true. But here I am not so sure about it, but option B is the more accurate. Okay, so this is the thing. Is it clear? Now let's move on to the this question. Which of the what is the computational complexity of the of computing the softmax function in the output layer of the neural network? Option A O n, option B O n square, option C O n log n, and option D O log n. So any guesses for this? No guesses, right? So yeah. So softmax function, this is the softmax function. We have e to the power zi and e to the power jz. Jz consists of all from 1 to n. That means you will have e to the power zi for class, like you have 3 classes: apple, banana, and let's say other fruit like pineapple. Okay, you have 3 classes. So whenever you want to find the softmax, the probability of banana, how you can find out? You e to the power z for banana class divided by e to the power z for this apple class, plus e to the power z for this apple, banana, and e to the power z for this pineapple class. Okay, that is how you find the softmax probability of this softmax probability or softmax function of this classification problem. Okay, so we compute this in three steps. One is to compute the exponential. Whenever we are computing the exponential, the complexity here is on. Whenever we are computing the sum, that is in the denominator, that the complexity is also on. And whenever we are doing the division operation, again the complexity is on. So overall complexity is on. Okay, so on is the correct answer. On square is not correct, because no nested loop or matrix multiplication is taking place. on log n is not correct because no sorting or logarithmic operation is not taking place, and o log n is not correct because logarithmic complexity usually arises in binary searches like tree structure. Whenever we will be doing the hierarchical softmax, there the complexity is o log n. Okay, otherwise the complexity is always o n, because here we are doing the simple operation like exponential, sum and division. For this the complexity is o n, and whenever we are doing the hierarchical softmax, there the complexity is o log n. Okay, so that is the thing. So this you need to remember. So option A is the right answer. Okay, so this is the thing. Now let's
One
move.
doubt actually.
Yeah, please.
You know, oh, you know, there are totally, you know, for computation, three times we are O of n, right? Three ON will be coming now. Why one ON is coming? The last, since each step is ON, the overall complexity remains same. They say. But
No,
actually, if you add the three one, you'll have three ON. Then how it is only one ON?
O3 and you are telling. No, computational complexity, it has only all this. Okay, on square, on log n on log n. Okay, that is a function of O. There is nothing called 3n. Okay, 3n means that is a function of n only. Okay, so that is why we write only on. Okay, so this is the thing. Whenever we are doing the simple operation like exponential, sum and division, all the we are having the complexity on. Okay, that is the thing. Whenever we are doing the this hierarchical softmax or binary search, there the complexity is o log n, and whenever we are doing the sorting operation, something like that operation, so this is purely of computer science, so there we have this complexity o n log n. And whenever we are doing the nested loop, that means loop inside loop, some computer program you must have seen, like loop inside loop are there the complexity is on square. Okay, so this is the thing. So that is why on is the correct answer. There is nothing called o3n. Okay, so this is the thing. Okay, so let's move on to the last question. How does hierarchical softmax reduce the computational complexity of computing the softmax function? It replaces the softmax function with a linear function. It uses binary tree to approximate the softmax function. It uses heuristic to compute the softmax function faster. Option D, it does not reduce the computational complexity of the computing the softmax function. So any guesses for this?
B.
It uses a binary tree. Yeah, it replaces softmax function with a linear function. No, this is false. It uses a heuristic to compute the softmax function faster. No, it does not reduce the computational complexity of computing the softmax. I have told you, for this hierarchical softmax, the computational complexity is O log n. Okay, so actually it is reducing the complexity. Okay, because what is greater? Okay, n is greater than log n. Okay, so that is why we are reducing the complexity in case of this hierarchical softmax function. So option B is the correct answer. Okay, option B is the correct answer. So in hierarchical softmax, instead of computing probabilities over the words, it models the vocabulary as a binary tree. Each word is a leaf node, and each internal node represents a probability decision. Predicting a word involves traversing a tree from the root to the leaf node, making a logarithmic number of binary decision. This reduces the complexity from on to o log n. Okay, so that is why option D is false, because it has been written it does not reduce. Okay, so this is the first thing. It replaces the softmax function to a linear function. This also does not make any sense. It uses a binary. Yeah, this is correct, and heuristic, this is also incorrect. Okay, so this is the thing. So option B is the correct answer. Okay, so this is the thing. So is it clear to all of you? So by this I am ending the session for today. Okay, and again I have given those codes in this DL code folder. Okay, so you can just see the DL code, and you can just find today, like, yeah, from this you can see from 31 to 35 one hot representation, then SVD word representation, then this continuous bag of words, skipgram and glove representation. Like one hot representation, you can see how we can encode our word to a one hot representation. So okay, I think it is slow. Yeah, so this is the thing, like this is our corpus of different word, apple, banana, orange, grape, apple, orange. So you can do the one hot representation. So apple will have, yeah, how many unique word we have? 1 2 3 4 only we have in unique word. We have a corpus of 1 2 3 4 3 3 6 word, okay, but we have only 4 word, 4 unique words, okay. So that therefore you can find do the one hot representation, okay. So the code is given to you, you can just copy the code to your drive and you can just see the results, okay. This is the one hot representation. Similarly other things are also given, so you can just open the code and you can see it, okay. So these are the thing. Also this is pure NLP, so somewhere the pre-trained model cannot be given because everything you cannot code, so therefore pre-trained models are there, so pre-trained model can be used. You just call the pre-trained model and you just give your input and just get your output, okay. So this can be done for this glove representation, or like glove representation only. I think I have given a pre-trained model. So pre-trained model, you just call the pre-trained model, you just give it the input and you can have the output, okay. So yeah, this is the thing, this is the pre-trained model, this is the glove representation pre-trained model. I have just loaded, and then we can just see the things, like, yeah, like you can see in the visualization, you can see this king and queen, this two words are similar to each other, so they are appearing close. This banana, apple, these two are very close to each other, so these two are appearing close. Computer science, yeah, these two are somewhat close. Car, bus, these two are close. Woman, man, these two are close, okay. So you can see the distance, this king and queen, the distance between king and queen, this Euclidean distance is small. Banana, apple, this Euclidean distance is small. Woman, man, this Euclidean distance is small, and car, bus, again this Euclidean distance is small, okay. So by that you can visualize how your model is performing, okay. So these codes are all I have given. You just copy the code to your drive and you can run the codes. Oh yeah, also another thing, some codes, what happens is, uh, yeah, this Google Colab, it gives you many option to run your code. One option is, yeah, you just open the runtime and you just change the runtime, okay. Sometime what happens is, the CPU is actually slower, okay. So you can just change your runtime to GPU, and whenever your model will be utilizing GPU, your code will run faster, okay. So this will help, okay. So what you do, you just open the code, copy the code to your drive and change the runtime to GPU, and then run your code. So by that you can run your code faster, okay. This also you can do. So this is the thing, okay. So by this ending the session for today, okay. Okay, by this I'm ending the session for today. We will meet the next Tuesday, okay.
Thank you, sir.
Okay, bye.
Thank you, sir. Bye.
Thank you, sir.
Okay, bye.